In this video, I will show you how to study the direction fields of first-order differential equations. Here we have a first-order ordinary differential equations. As we know, the graph of a solution of this equation is a curve. The tangent of this curve at the point xy is exactly the value of f at that point. Okay, this is easily follows from the geometric meaning of derivative, because the left-hand side is precisely the slope of the tangent of the curve. Okay. Now, at every point, we can draw some small segment which this slope fxy. So all these segments forms the direction field of this ordinary differential equation. And the direction field are very useful. Using direction field, we can observe some quantitative properties of the solutions. This will enhance our understanding of the solutions and the ordinary differential equation under consideration. But by definition, to draw the direction field, we have to compute the value of f at many points and draw the many small segments which that values as slopes. That's a very complicated job. Fortunately, there are some computer softwares and even some web page which will make this job very easy and convenient. Here I will recommend you this web page called Slope and Direction Fields. Okay. The link to this web page had been added to the page of our course. You see here is a useful link. The first link will direct you to this page, and when you click this link here, you will go to the page I just mentioned. Okay, that is this page. This page was constructed by a professor at this university, Bluffton University. His name is Nestor, Daily Nestor, at the bottom of this page. This is the owner of the web page. Thank you. Thank him for build this wonderful page for us. Okay. Now I will demonstrate you how to use this web page to construct direction field by the following example. We consider this ordinary differential equation. This is a nonlinear equation. So how to study this equation? Of course, this equation is solvable. We can solve this equation by integration, but the computation will be very tedious if we just want to obtain some quantitative properties. We don't need to solve the equation, right? So as we can see, we'll make dy dt equal 0. Then y is 0 or y is 2. So these two constants, 0 and 2, are constant solutions of the equation, as you can check. These equations are called equilibrium solutions. Okay. Now, if y is non-negative, then dy dt is also non-negative. So this means y is an increasing function. Similarly, if y is negative, then dy dt is negative and y is decreasing. Can we have a more clear picture about the behavior of the solutions of this equation? Okay, then we go to the web page to consider the direction field. In this page, the left upper corner, we can enter the right-hand side of the equation. In our case, the equation is dy dt equal y minus 2 square. So we can change the name of the variable dy dt. Okay, and then enter the right-hand side, y multiply y minus 2 square. Okay, and when we press enter, the right half of the screen become like this. There are many small segments. These small segments consist of the direction field of our equation. Okay, and here we have several boxes. We can enter some value in these boxes to control the range of the variable t and y. Here t is -4 to 4 and y is -3 to 3. We can, for example, we can change this value t -2 to 4, y also y -3 to 3. That's okay. Okay, and here segments. These two boxes control the number of segments in t direction and the y direction respectively. The maximum is 30. Obviously, if the segment, the more the segment, the clearer the picture is. So we can try both of these to be 30. Okay, then you see the direction field become like this. This is much finer than the previous one. Okay, so here the entry ty enter ty here. In these two boxes, we can enter the initial value to construct to display the integral curve of the corresponding initial value problem. For example, as we mentioned before, y equal to 0 is a solution. So we can take this to be 0, 0. This means when t equal to 0, y is also 0. Press submit. We will get a corresponding integral curve. So this is this red one. This is y equal to 0. This is the first constant solution of our equation, y equal to 0. Similarly, if we take y equal to 2, we will get another equilibrium solutions of our equation. This green curve, okay, this green curve is the curve corresponding to y equal to 2. So these two are two integral curves of our equation, which is the corresponding initial value. And how about y equal to 1 at 0? Okay, submit. Okay, this blue curve is the curve which initial value at 0, y equal to 1. And in this manner, we can have many solutions, many integral curve. Maybe I will change the range of y, not 3, maybe 6 will be better. Okay, so the picture, I increase the range of y to maybe 5 will be fine, better 5. Maybe 5 is good. Okay. Now we consider the other integral curve. We have those 3 integral curve, 2 of which are the equilibrium solutions. Okay. Now we consider the curve integral curve which initial value greater than 2. For example, 2.5. Maybe this. Maybe 3. Okay, so this is the curve, integral curve, which initial value 3 here. Okay, also we can consider integral curve which negative initial value at 0, maybe minus 1. Okay, so this curve intersect with the vertical line. The coordinate of this point is the initial value. T equal to 0, y equal to -1. But as we see, this curve is not very smooth because these curves are drawn by discretization. So there is a step h here. The h here is 0.1. Maybe this, if the curve is not smooth, we can decrease this step h. The h is when h becomes smaller, the curve will become smoother. Therefore, we replace this h by 0.01 and click here to switch. So the curve will become smooth. Wonderful. Okay, and we can also obtain the other integral curve just by click anywhere in the screen. For example, I click here. I will get an integral curve passing this point. Similarly, I click here, I will get this black one, which is an integral curve passing the point I clicked. Of course, I can click here to get many integral curve. So we have a very complete picture of the behavior of the solutions of our differential equation. Now, can we have some conclusion? So from this picture, we see that if the initial value is less than 0, then this curve is decreasing. The corresponding solution is decreasing, and it seems that the solution will be unbounded below infinite time, because all this curve goes to negative infinity. And for the solutions which initial value between 0 and 2, between these two equilibrium solutions, and we see that the corresponding solution will approach y equal to 2 when t goes to positive infinity, okay, like this one, okay. And we can also see that it seems that all this curve, which initial value between 0 and 2 will approach to 0 when t goes to minus infinity. Okay, we have this conjecture. And for the initial value greater than 2, for solution corresponding to initial value greater than 2, like this yellow one, and many others, we can see that those solutions will be unbounded infinite time. Okay, so this gives us a very clear picture of the behavior of the solutions of these differential equations. Okay.